Long-range air defense systems have proliferated rapidly over the past several decades, with even many second-tier military powers acquiring increasingly sophisticated capabilities. To counter these threats, the United States has invested heavily in the development of anti-radiation missiles, ARMs, weapons specifically designed to detect, track, and destroy enemy radar emitters and other radio frequency sources. The AGM-88 HARM, high-speed anti-radiation missile, entered U.S. service in 1983 and became a cornerstone of suppression of enemy air defenses, SEAD operations. Its successor, the AGM-88G AARGM-ER, Advanced Anti-Radiation Guided Missile Extended Range, entered low-rate production in 2021. India has pursued a similar path through the development of the indigenous Rudram family of anti-radiation missiles. Rudram-I became the country's first domestically developed ARM, marking a major milestone in India's efforts to reduce reliance on imported weapon systems. Building upon that foundation, DRDO developed the longer-range and more capable Rudram-II. A successful flight test conducted in June 2026 demonstrated the growing maturity of the program and underscored India's progress toward fielding an indigenous long-range SEAD capability intended to eventually replace imported Kh-31 anti-radiation missiles in Indian Air Force service. In this video, Defense Updates analyzes how India's Rudram-II compares to American AGM-88G AARGM-ER. We will examine 5 categories and then draw a conclusion. Before we proceed, a word on NordVPN, which is one of the most trusted and fastest VPN brand that has a no-log policy validated by Deloitte. NordVPN provides a 256-bit encrypted tunnel that protects your privacy and also enables you to access contents that are blocked based on geolocation. Its threat protection system helps you avoid phishing, scams, and malware. NordVPN application is available for all the major platforms as well as browsers. Get an exclusive NordVPN deal with massive saving by going to nordvpn.com/defense or clicking the link in the description. It's risk-free with Nord's 30-day money-back guarantee. When it comes to engagement range, both the Rudram-II and AGM-88G AARGM-ER represent a major leap over previous generation anti-radiation missiles, enabling launch aircraft to prosecute enemy air defense targets from well beyond the reach of many surface-to-air missile systems. Rudram-II is believed to possess a maximum range of up to 350 kilometers, 217 miles, placing it among the longest-range anti-radiation missiles currently under development. The American counterpart, meanwhile, has an officially acknowledged range exceeding 300 kilometers, 186 miles, although its true maximum reach remains classified. Based on publicly available information, the two missiles appear broadly comparable in terms of standoff capability, with Rudram-II potentially enjoying a modest advantage in outright range. The differing approaches taken by the two programs are also noteworthy. Rudram-II achieves its long reach through a larger airframe and powerful propulsion system optimized for extended range engagements. In contrast, the AARGM-ER combines a redesigned low-drag airframe with an enlarged rocket motor, delivering a substantial increase in range while remaining compact. This is basically a tie. The Rudram-II and AARGM-ER take notably different approaches to survivability and target engagement. Rudram-II is reported to employ a high-speed quasi-ballistic flight profile and is estimated to achieve terminal velocities of approximately Mach 5.5. Such speeds can significantly compress an air defense system's engagement timeline and increase the missile's kinetic energy upon impact. The AARGM-ER, by comparison, is believed to achieve speeds in excess of Mach 4. While this is lower than the estimated terminal velocity attributed to Rudram-II, the missile compensates through a different operational concept centered on low-altitude penetration. By remaining closer to the terrain for much of its flight, the AARGM-ER can exploit radar horizon limitations and reduce the amount of time available for defenders to detect, track, and engage the incoming threat. The contrasting flight profiles present distinct advantages and disadvantages. Rudram-II's quasi-ballistic trajectory allows it to retain high terminal energy and potentially achieve longer reach. But the missile's climb to higher altitudes may increase its detectability during portions of its flight. In contrast, the American missile's lower altitude approach generally offers a smaller radar exposure and can complicate interception efforts, particularly against air defense systems constrained by line-of-sight limitations. Given the fact that AARGM-ER is pretty fast and the profile makes it much more obscure, it has the advantage. The two missiles employ broadly similar concepts during the initial phases of engagement, relying on passive radio frequency homing, inertial navigation, and satellite-assisted guidance to prosecute enemy radar emitters. Both missiles are designed to counter a common defensive tactic in which radar operators shut down their emitters immediately after detecting an incoming anti-radiation missile, allowing the weapon to continue toward the target's last known location, even after emissions cease. The principal distinction lies in the terminal guidance architecture. Based on publicly available information, Rudram-II appears to rely primarily on passive RF sensing, combined with navigation-based guidance to engage targets after radar shutdown. The AARGM-ER, however, incorporates a more sophisticated multi-mode seeker suite that combines passive anti-radiation homing, GPS-aided inertial navigation, a two-way data link, and a millimeter wave MMW radar seeker. The addition of the MMW radar seeker provides the AARGM-ER with a significant advantage against modern mobile air defense systems. While conventional anti-radiation missiles generally depend on the target continuing to emit or remaining near its last known location, the AARGM-ER can actively search the target area during the terminal phase and identify physical objects such as radar vehicles, transporter erector launchers, command vehicles, and associated support equipment. The capability is particularly relevant against modern shoot-and-scoot air defense networks, where radar systems shut down and relocate shortly after detection of an incoming threat. Viewers may note that this capability was designed specifically to counter Russian S-300 and S-400 batteries that are mobile. So, AARGM-ER will generally possess a higher probability of successfully prosecuting moving targets. The two missiles reflect two distinct approaches to target destruction. Based on publicly available estimates, Rudram-II carries a substantially larger warhead of up to approximately 200 kilograms, 440 pounds, nearly 3 times the size of the AARGM-ER's roughly 70 kilograms, 154 pounds, blast fragmentation payload. This significant difference in explosive mass suggests that Rudram-II places a greater emphasis on delivering maximum destructive power against a broad range of air defense assets. The larger warhead is expected to provide Rudram-II with the ability to inflict severe damage not only on radar antennas and fire control systems, but also on associated command vehicles, missile launchers, hardened facilities, and supporting infrastructure. Such a design philosophy prioritizes overwhelming destructive effect and the potential to neutralize multiple elements of an air defense site with a single strike. The AARGM-ER, by comparison, relies less on explosive yield and more on precision target engagement. Both approaches are capable of suppressing or destroying enemy air defenses, but Rudram-II is likely to cause more damage, and even near misses could be crippling. The integration of the two missiles reflects the differing design philosophies of the aircraft in missile combinations they are intended to equip. The F-35A and F-35C are expected to carry up to 4 AARGM-ER missiles internally, with 2 weapons housed in each internal weapons bay. This configuration allows the aircraft to retain its low observable characteristics while carrying a substantial anti-radiation missile loadout, enabling it to penetrate heavily defended airspace without compromising its stealth profile. Further, Boeing EA-18G Growler, the U.S. Navy's dedicated electronic attack and seed platform, can carry 4 of these missiles. By comparison, the Su-30 MKI is believed to be capable of carrying up to 3 Rudram-II missiles. Based on available information, a typical configuration would likely consist of 1 missile mounted on the centerline station and 1 missile carried under each wing root heavy weapon station. The lower missile count primarily reflects the significantly larger size and weight of the Rudram-II, which occupies more space and requires carriage on the aircraft's strongest hardpoints. Rudram-II will also be integrated with Mirage 2000, likely carrying 2 missiles. The fact is, AARGM-ER is compatible with more sophisticated combat platforms compared to Rudram-II. While Rudram-II appears to be a highly capable long-range anti-radiation missile, the AARGM-ER benefits from a significant advantage in maturity. It represents the culmination of more than 4 decades of operational experience gained through successive generations of U.S. anti-radiation weapons, from the AGM-88 HARM to the AGM-88E AARGM, and ultimately the AARGM-ER. This evolutionary development process has produced a weapon that is not only technologically sophisticated, but also backed by extensive testing, operational validation, and real-world combat experience. Further, the effectiveness of a seed campaign depends on far more than the missile itself. Success is determined by the broader ecosystem of sensors, electronic warfare assets, data networks, intelligence platforms, and launch aircraft that support the weapon. In this regard, the United States maintains a substantial advantage. F-35 plus AARGM-ER enables penetration through stealth and excellent situational awareness. EA-18G Growler plus AARGM-ER enables penetration through electronic attack. Together, these platforms significantly enhance the effectiveness and survivability of the AARGM-ER, making the overall system far more lethal than the missile alone would suggest. Rudram-II, by contrast, will be fielded primarily aboard fourth-generation platforms such as the Su-30 Mki. Consequently, although Rudram-II may offer impressive range, speed, and destructive power, its operational effectiveness will be influenced by the limitations of the platforms and supporting ecosystem available to employ it.